In this video, we're going to look at hydrates. You've used hydrated compounds, and you probably didn't even know it. A lot of ionic compounds naturally exist in a hydrated form, which means there's water molecules kind of loosely embedded in the crystal structure. I like this visual here. An ionic compound should have a tightly packed crystalline structure. Everything's very organized. There's repeating patterns of positive and negative ions. But now there are these little water molecules gently embedded within the crystal structure. Later on, we're going to do a lab with hydrated compounds. We're going to heat them gently. And all we're doing is dehydrating the hydrate. If you heat the hydrate gently, all you'll do is evaporate the water. So now what's left is called the anhydrous salt. Just the ionic compound without the water molecules. Now we have to be careful that we heat them gently, otherwise we can start decomposing the ionic compound. That's not what we want to do. A lot of these hydrate formulas will look very similar to their original formula that you're familiar with. Copper sulfate is a real common hydrate. You've probably used copper sulfate in the lab before. It's like a really pretty blue crystal. Copper sulfate often exists in a hydrate form. To write the formula and the name, the anhydrous salt just looks like any other ionic compound. So this part here is called the anhydrous salt. Anhydrous meaning without water. Now in the formula, you're going to see this big dot and then a certain amount of water molecules. That dot just means that the water molecules are loosely bonded to the original salt. That if I heat this gently, I can remove these 5 water molecules and not change the structure of the copper sulfate. And that's one of the errors that we'll kind of look at in the lab. If you overheat this thing, you could start decomposing the copper sulfate, and we wouldn't want to do that, but we could remove the oxygen from the sulfate, and then we're going to be in trouble. So we don't want to do that. Sometimes people will accidentally think that the dot somehow means multiply. So let's say we were finding the molar mass of this hydrate. They'll take copper plus sulfur plus 4 times the mass of oxygen, and then somehow they multiply that by 5 times the mass of water, and they get this crazy giant molar mass. We would really just add. If I wanted the molar mass of this hydrate, I would take the mass of the copper sulfate plus the mass of 5 water molecules. So they're just loosely bonded together. That's what the dot means. Visually, this is what I'm thinking about in my head, that here's this copper sulfate unit, and surrounding that copper sulfate would be 1, 2, 3, 4, 5 water molecules. 5 water molecules. I think we kind of mentioned before, copper sulfate's a really pretty blue crystal. When you drive off the water, it changes color. It'll turn white. There's kind of a packer one that we'll look at. It'll start out green, and when you dehydrate it, it turns gold. So that's kind of a key. We'll look at the color change in the lab, and then we'll know when to stop heating. When we see that it's all changed colors, stop the heating process. If they turn like brown or black, then we're starting to decompose the original salt. The amount of water in the hydrate is noted with a prefix, and these are all the prefixes that you would have probably guessed. If you have 1 water molecule, the prefix would be mono. So we'd say monohydrate. 2 water molecules would be dihydrate. 3 is tri. 4 is tetra. 5 is penta, as is with this copper sulfate. Pentahydrate, 5 waters for each copper sulfate unit. 6 is hexa. 7 is hepta. 8 is octa. 9, you can spell it either way. Nano or nano. Nanohydrate or nanohydrate. And 10 would be deca. That's a C. I should make that nicer. DEC. Decahydrate. So there shouldn't be too much that goes into naming these compounds that you haven't done before. You'll have the salt first, and I name the salt just like I would any other ionic compound. I've got CuCl2, copper chloride, copper chloride. Copper is in the transition metal family in the middle of the periodic table, which means if I don't note the charge with a Roman numeral, nobody's going to be able to write the formula. I don't know the charge on copper. Copper can have multiple charges, so I kind of need to work backwards. I know chlorine's charge will always be -1. There are 2 chlorine in the compound. There's only 1 copper. So on the back side, I'm going to have a charge of -2. The copper must be +2. Copper 2 chloride. And now I use one of those prefixes to say how many water molecules are present for each copper chloride unit. This is 2 water molecules, dihydrate. There, piece of cake. If I want to write the formula, again, not a big deal. Sodium is always in the group that's +1. Sulfate, ATE, polyatomic. Sulfate is SO4 -2. So I want to make this neutral. We're going to need 2 sulfates. SO4. When I write the formula, you'll see that big dot in the middle. Decahydrate means 10 water molecules. You do not need to put the big dot when you're writing the name out as words. Then you can just say copper 2 chloride dihydrate. That's fine. The big dot just comes when you see the formula written as symbols. So these hydrated compounds are actually pretty common. We'll definitely use them in the lab. But they really shouldn't pose any difficulties when it comes to writing their formulas or writing their names.